All right, so here we're in the last video focusing around conductors. In this video, we're going to look at equipotential surfaces because this is a very common question that pops up when you connect two conducting spheres by a wire. Okay, and so first, let's just talk about a quick technology that actually uses this principle, and that would be the Faraday cage. Right, and so if I take a conducting metal piece and put it into an electric field, what happens is whatever's inside is essentially shielded from that E field, right? And so this is what we call a Faraday cage. And so electrostatic shielding, right? And so through the process called electrostatic shielding, a region is rendered free of electric fields. Shielding occurs when a conductor is placed in an electric field and the excess charges rearrange themselves to directly counteract the field and thus shield the interior of the cage from the external field, right? And so basically what it does is it cancels out the electric field inside, right? And so if this is a positive field, all these they align themselves negatively on the outside and they block, right? They cancel out that field as it's coming in. Okay, and so um, electrostatic induction, right, is the process by which a countervailing electric field is induced. Now, the more important question that they talk about here is two conducting spheres. So the two conducting sphere problem is a very common problem that can be seen on the AP Physics C, E, and M test. So basically what you have is you have a sphere of radius r, right, connected, all right, with a charge q connected to a sphere, another sphere, and we'll call this RA, right? Typically the other one is smaller or bigger, right? So there's going to be a difference in the size. Um, with no charge by a conducting wire, and the system is allowed to come to equilibrium. The problem can ask you to find the charge on each sphere, right? So first, the problem will state that the surface and the interior of a conductor are all the same potential. So that you have to, so it's going to happen. It's going to create an equipotential surface, right? So they are in equipotential surface. So they basically become one giant conductor, all right? And that charge ultimately does get distributed equally throughout, all right? And so the electric potential we can find by using KQ over R. Okay. And so what happens is the total charge gets distributed amongst the two. Okay. And so so here we go. Here's an example problem. So an isolated spherical conductor of radius RA, and it has a charge of Q on it. A second isolated spherical conductor of radius RB, which is 1/2 of RA, has no net charge. The spheres are now connected by a conducting wire and the system comes to equilibrium. What is the ratio of the surface charge density on sphere A to sphere B? Okay. And so we know that the surface charge density, right, because ultimately we're looking for what is the ratio of these two, is going to be QA over 4 pi RA squared, right? Because it's just simply charge over area. So we got QB over 4 pi RB squared, right? But we know that this is going to be 1/2 of RA, okay? And so I did forget to type something here. We want to answer in terms of Q, RA, and RB if necessary, okay? Um, and so we're looking for the ratio. So we're going to say sigma A over sigma B. So it's going to be QA over 4 pi RA squared over QB over 4 pi RB squared, right? And so the 4 pi's would cancel out. So we end up with QA over RA squared over QB over RB squared. Okay. If you want to clean this up a little bit, you actually end up with like QARB squared over QB over RA squared, right? If I do a little bit of math here, but we know that RB is 1/2 of RA. You can put that in there here if you want. You can also say that um, you may find the ratio somewhere else. So let's look at, we know these are equipotential. We need to figure out basically what is this ratio right here, right? And that's going to come from our equipotentials, right? And so I'm going to say VA equals VB, right? Equipotential just tells me that the potential difference is going to be the same. Okay, so these k's would cancel out. If I do a little bit of algebra, I get QA over QB equals, right? So bring that down, bring that up. I get RA squared over RB. It's not squared, sorry. It's just R. Okay. But I know that there's a ratio. We know that RB, right, is 1/2 of RA. And so what's QA to QB? It's just 2. Okay. And so now I can also plug that ratio in here, right? So I get 2. Now RB is 1/2 of RA, but here I'm going to square those. Okay. And so I get 2 times 1/4, right? Because RA, so this ends up being 1/4 if I square it. RA squared over RA squared cancels out. So my ratio of sigma A to sigma B is going to be not 2, but 1/2. Okay. Or you can say that 2 sigma A equals sigma B, right? And you know, sigma is QA over, right, is, sorry, QA is 4 pi RA squared, and QB or sigma B is QB over 4 pi, right? But we know the ratio is going to be 1/2. All right. So in the next video, we're going to start, unit 2.2, which is going to be capacitors.